Greetings, colleagues. My goal today is to give you a very focused analysis related to some recent research we have been doing within the broad themes of this conference. The analysis focuses on the great agrarian transition, which is essentially the acquisition of large tracts of land by private interests. And often this is being done for cash crops, but also for industrialized food production. What I'm going to focus on is an analysis of the energy part of the nexus and the potentials for that in terms of cleaner production and mitigation of climate impacts. So, within the broad theme of the food, energy, water nexus, this is perhaps a neglected area of work which I thought would be particularly pertinent for this conference. It's brand new data, and we're still in the process of doing further analysis. And so, we would welcome your input using my email related to the United Nations International Resource Panel on which I serve, and also in my academic capacity as well as a researcher. So if you need to send feedback, please do so by email. You're also welcome to follow me on social media, and my more detailed bio is linked there for you as well. So, in terms of background, first of all, it's important to recognize how much of the world's energy is being used for the modern food system. It's a staggering amount in terms of fossil fuels, 30% of the world's energy, of which 10% is being used at the farm level. Now, more specifically, if you go into fertilizer production, 2% of the world's energy is used specifically to produce reactive nitrogen, which is termed NR. And this is done through the very energy intensive Haber-Bosch process. And this goes back to a very old technique, and it's largely through that process that reactive nitrogen prices are closely coupled to human needs if you go back all the way to the 19th century when this kind of industrialized fertilizer production started. It's important to note that industrialized agriculture has relied on both mined sources of nitrogen and phosphorus, both nitrates and phosphates, from deposits in minerals. But it has also, especially with regard to nitrogen, reactive nitrogen, relied on the Haber-Bosch process, which is able to harness unreactive nitrogen gas that is more than 70% of our atmosphere and convert it into reactive nitrogen compounds, which can then make essentially ammonia and ammonium related fertilizer. Now, zooming out into what I'm referring to as the Great Agrarian Transition, let's consider also what we mean by great transitions. The term Great Transition goes back to the work of the economist Kenneth Boulding, who wrote a book titled Meaning of the 20th Century, The Great Transition. And he highlighted the pivotal role the 20th century has played in terms of transformation of human impact on the planet. And that's why we often refer to now the current sense of geologic time as the Anthropocene. And it's something that has even gained currency among earth scientists because of the primacy of human impact. There are also other transitions that have been happening in terms of industrialization. The World Economic Forum has popularized the term the fourth industrial revolution, considering the other three. First of all, the first industrial revolution was the steam engine and the use of coal for steam. The second industrial revolution was electricity and the use of electricity for such a vast array of energy delivery. And the third industrial revolution was the advent of the computer and the Silicon Age, allowing for massive processing of information. And the fourth industrial revolution is the networking and the interdependence of social and technical systems through infrastructure such as the internet and broader globalization pathways. Now, within this context, there has been a recognition from a lot of environmental thinkers and planners that we should be considering these transitions integratively. And a more normative perspective is provided by the Great Transitions Initiative, which started with the Telus Institute. And you can refer to further details on that at this website, greattransition.org. So I'm going to focus on specifically the great agrarian transition, which is manifests most acutely through these large land acquisitions, sometimes of virgin land of forests, sometimes of small landholders, farmers, sometimes of brownfields. So it's a vast kind of mix of acquisitions. And secondly, there is an energy transition too that's happening, a move towards renewable energy, but often higher intensity and greater devolution of usage of energy is happening. So with lots of different products and hence the need for batteries and so on as well. So there is this energy transition and the agrarian transition that's happening together, which is putting pressures at the local level where communities need both food and energy and indeed cash crops as well. Now, this is some analysis which we have done looking at a data set that was prepared by colleagues in Switzerland called the Land Matrix data set. And this is open source, freely available for those of you who would like to do further research from this data set. It looks at all of the global private land acquisitions that have happened and tries to categorize them by crop and a range of characteristics. So what we did here was we basically looked at a focused range of crops for which we have some further information on industrialized agriculture and also the use of fertilizers. And this is what the profile looks like. There's a very large percentage of the acquisitions that are being used for palm oil production. There are also forests that are being grown, hence the term trees that's presented there. Then we've also categorized rubber trees separately because of a particular aspect of that particular crop. What you have in the small numbers there in the bottom is it's the acreage as an absolute amount of the total 4.7 million hectares that are in this private land acquisition profile that we have got from the Land Matrix data set. So that gives you the absolute amount of the hectares for each crop. And what we then did was we used some data on per unit fertilizer energy usage that comes from work done by David Pimentel as well as some other sources where he compared the use of fertilizers in terms of energy usage and also with organic farming, comparing if there was manure being used. And we're referring to the conventional or industrialized agriculture as intensive and the other non-conventional smallholder as well as other farmers who are not using the industrialized fertilizers as extensive. And the fossil fuel energy input in gigajoules per year is striking in terms of the intensive versus the extensive usage. What you find is also that food crops are a major segment of the fertilizer usage, more than half. And you also have cotton and oil palm playing a significant role, but perhaps not as much as one might have expected initially. Now, this data is showing you the low input and high input fertilizer usage in terms of the crop itself. And here, what is interesting is that the growth of oil palm, for example, and jatropha, which is similar kind of product, does not itself use too much in terms of energy for the high input production, meaning industrialized productions of large plantations versus smallholder plantations. But for a crop like cotton, you have much higher differential in terms of the industrialized version of cotton. We've put these green bars for oil palm because there is also a major energy usage in processing the oil. And we got these estimates from a review of literature on processing of the oil palm and making it ready for production. The same could be done for some of the other cash crops as well. but we thought it was particularly appropriate for oil palm because it's going into a food product immediately therein. The same could be said of sugar beet, but sugar beet often is also going into biofuel production. So this is giving you a profile so that one can think about the ways in which we can encourage farmers to use more targeted policies for crops that are less energy intensive in certain areas, and where there may also be opportunities for less usage of industrial fertilizers. Now, it's important to consider that there is a transition happening for large scale uh, industrialized organic agriculture, which is significant. And we need better geospatial analysis. This is going to be the next phase of our work, where we're going to try and understand before and after, and also get usage data on fertilizers for large scale land acquisitions more directly. Right now, that is a work in progress. We would welcome your input on that. It will also help us understand economies of scale for organic agriculture and how that links to energy usage. But we are also concerned about not greenwashing this issue. Just because you can have large scale organic farming and you reduce the energy usage per hectare, you still have to think about issues of energy sovereignty and justice for those landholders who has that ability to make a decision in terms of how the land is being used, where the energy is coming from. There's also a very important aspect of the water energy nexus with regard to this whole transition, because many times groundwater is being used for irrigation, even for organic agriculture. And in that case, you have pumps that are needed, and you have a range of energy inputs which can make a difference in terms of the energy sovereignty and justice for the communities involved. So that's another area that we are working and doing further analysis on. The food versus cash crop dichotomy is significant altogether. And as we move towards other forms of urban agriculture, particularly greenhouses and using urban infrastructure for producing food, that will be an area that becomes even more salient. So, this is going to be linked potentially to the whole sustainable cities discourse as well. So, this is a work in progress which we feel deserves much more attention as these large scale land acquisitions gain traction. I'd like to acknowledge the support of the Socio-Ecological Synthesis Center, or SESINC, of the US National Science Foundation, that has provided support for us to engage with multiple stakeholders. It's a grant that has been led by Professor Jean-Paul Angelo and Professor Paolo Diodorico at University of California, Berkeley, as well as my other colleagues who are noted here, who have specifically helped with this part of the analysis. And we have several other teams who are looking at other aspects of the large scale land acquisitions impact on this great agrarian transition in terms of the biodiversity impacts, for example, and other issues. So stay tuned. In the next year or so, we will hopefully have a range of publications coming out, and we would love to engage with the cleaner production community in this regard. Thanks to all of you, and all best wishes.